Magnetostatics, forces on current elements. We have a lot to talk about in this lecture, but first we'll set up the problem for talking about force on a current element. So imagine a wire meandering through some kind of magnetic field. We need to set ourselves up to do some kind of integration along that wire to calculate the total force on that wire. From there, we'll move to having two current elements. So imagine two wires. One wire produces a magnetic field, and then that puts a force on the second wire. And that assumes both wires are carrying currents. Then we'll look at a case where those current elements are actually loops, and some special things happen there. And that'll bring us into talking about magnetic torque and moment. And it turns out a loop in a magnetic field won't change its position, but it will rotate. The magnetic field puts a torque on the loop instead of a force to move it in a particular direction. And we'll end with a quick discussion of a magnetic dipole. Force on a current element. So here's our setup. We're in Cartesian coordinates x, y, z. And then I place a differential current element at some arbitrary position, and I put that current element in an arbitrary direction. We'll then embed that in a magnetic field that's also oriented in yet another arbitrary direction. It turns out that magnetic field will put a force on that differential current element. Now, because it is a differential current element, that force will be a differential force. And the equation describing that is given on this slide. We're going to derive it next. Now, there's a cross product here. That tells us that the force on that current element will be perpendicular to both the direction of the current in that element and the magnetic field. Now, the current and the magnetic field do not need to be perpendicular to each other. They can't be parallel or the cross product goes to zero. But there's no requirement on the orientation of magnetic field and current element. It's just because there's a cross product, the force will always be perpendicular to both the current and the magnetic field. So let's go ahead and derive that equation for the differential force. So we start off with the Lorentz force law, and we're ignoring the electric field part of that. So F equals Q times U cross B. To get the differential force, we'll differentiate that equation. And we end up with a term here, dq times U. So what is that? Well, dq is a differential charge, u is velocity, so this is some kind of moving differential charge. It is a differential current. So that takes us back to the differential currents that we discussed. We talk about the Biot-Savart law, one for line currents, one for surface currents, and one for volume currents. Let's look a little bit more deeply in the volume current term. So current is simply charge moving at some velocity. So J equals rho times U. Now we can swap U and dV to have rho dV inside of the parentheses, multiplying U. Well, we know this is a differential current. We also know up here is a differential current. And if we compare these terms, we see that dq is rho v times dv. So we can replace the rho sub v dv with dq. So altogether then, we can say that if we, for our thin wire example, and our little differential current element is a thin wire, that IDL is the same as dq times u. So there's our conclusion, IDL equals dq times u. So this is really saying that our differential current element is like differential charge moving at velocity u, and that dqu is really a convection current, but it is equivalent to the conduction current IDL. So that's where we were. We had our differential force equals dqu cross b. So since we have this equivalence of IDL and DQU, we can replace DQU with IDL, and we arrive at the equation we presented at the beginning for differential force. Now let's think about the total force on a wire. So it's a thin wire, and we're going to need to integrate that differential force over the entire length of the wire. So our general integral is written this way. Well, we just derived an expression for the differential force. We can put that in our integral, and we arrive at the general expression for calculating the force over the length of a wire. Now let's think about the force on a surface current. Again, go back to these differential currents that we derived or talked about when we were discussing the Biot-Savart law. So it's really not a surprise then that when we integrate over the area of that surface current that we end up with a surface integral integrating k ds instead of IDL cross B. And of course, we're integrating over a surface. So it's really just a matter of swapping IDL out for KDS, and then of course integrating over a surface. And then again, even less surprise, when we have a volume current, we replace IDL with JdV. And of course, now we have a triple integral because we're integrating over a volume. So now we can calculate force over line currents, surface currents, and volume currents. I'll mention once again, the volume current is really the only thing that's physically real, that physically exists. The others are just mathematical simplifications. And very often when we have a thin sheet or thin wire, those are really good approximations. But make no mistake, this volume equation is the only thing that is physically real. Let's work a quick example to just get a feel for the numbers. So if we have a typical kitchen magnet, this is something that you have sticking to your refrigerator. If we put that up next to a wire that's 1 inch long and it's carrying 1 amp of current, that's pretty reasonable. What kind of a force does that kitchen magnet put on that wire? So first, we have to know what kind of a magnetic field a kitchen magnet puts out. And it turns out it's about 5 millitesla. Clearly this varies a bit depending on your kitchen magnet. But it's a good average number to use. So the force, we'll have to integrate IDL cross B over the length of the wire. And we can make an assumption that we will put the magnetic field so that the field is perpendicular to the current in the wire. That really simplifies the math. And our integral just reduces down to IBL, current times the magnitude of the magnetic field times the length of the wire. And so we can plug in all of our numbers and we get the force, 127 micronewtons. Well, what is that? It turns out it's about 1/100th of the weight of a penny. Force between two current elements. So to handle general problems where we're integrating over two different wires or two different surface currents, we need to be able to calculate the force of one little differential current puts on another differential little current. So here we're showing two differential currents, the current 1 and current 2. Now the differential force that one puts on the other, since we have a differential current element, it's a differential force, but since that differential force is being applied to another differential current element, really that force ends up becoming a double differential. Physically what's happening is the first current element is creating a magnetic field, and that magnetic field then puts a force on the second current element. So let's go ahead and derive an equation for this double differential force. So we start off with the second current element, and that is going to put off a magnetic field. So we can use the Biot-Savart law and write an expression for the magnetic field put off by that second differential current element. Now, we need to figure out the force that puts on the first current element, but we need the magnetic flux density B for a force equation. So we just calculated H that the second current element put out. We convert that to the B field put out by that second current element using the constitutive relation. So we divide by mu. And so we end up with differential B2 equals essentially the Biot-Savart law, but there's the permeability term sitting there. Now that we know the magnetic field put off by that second current element, we need to calculate the force that puts on the first differential current element. However, we've written B2 here, and we don't really have B2. We have the differential of B2 because it was generated by a differential current element. So we can get a differential of B2 simply by differentiating this equation. So we differentiate, and now we have a double differential for our force. And on the right-hand side, our differentials applied to B2. But this dB2 is something that we derived on the previous slide. Remember, this was essentially just the Biot-Savart law, but with the permeability sitting here. The permeability is there because we're calculating a B field instead of an H field. Well, we can plug that expression in, and we have a bit more complicated expression now for our double force, and we have an IDL1 cross IDL2 scaled by the permeability cross an A21, which is a unit vector in a direction connecting the two current elements. So that really was our equation. There's two common forms that this is expressed. Usually the permeability is brought to the outside, and now we can see it's IDL1 cross IDL2 cross the unit vector. Or we can also bring out I1 and I2 so that it's just DL1 cross DL2 cross the unit vector connecting the two current elements. And this one maybe looks a little bit cleaner. So that's really our final expression for the double differential for force. It's a double differential because our first, or in this case we did it, our second differential current element put out a differential magnetic field. A differential magnetic field will then put a double differential force on another differential current element. The reason we're doing this is so that we have something generic that we can integrate over both current elements. That's why we did this. So if you remember Coulomb's law, we had two charges. One charge put out an electric field which put a force on the other charge. This equation is the equivalent of Coulomb's law in electrostatics. So it's kind of like a Coulomb's law for magnetostatics, but there's no charges, it's currents, and then there's cross products and all that happening here. So here's an animation of this double integration that we have to do to calculate the force between the line currents. So we imagine L2, this wire L2, puts out a magnetic field that induces a force on the first current element. However, they're twisted, bent pieces of wire. So the way we really think about this is looking at a specific line current on L1, we integrate that against all of the differential line currents on L2 because each one of those puts a slightly different force on that current element in L1. And we have to add all those up. Once we add them all up, then we have the total force at that particular line current. Then we move on to the next line current. And then we add up all of those integrated forces, if you will, to get the total force on L1. I feel like I did a really horrible job of explaining that, but that's the visualization of a double integral. And so here could be a final equation if we plug in the equation from the previous slide. The permeability, the two currents are constants. They can come to the outside along with the 4 pi. So really we're just left with DL1 cross DL2 cross the unit vector that's connecting our two current elements that we happen to be integrating, divided by the distance between them squared. Let's work an example, a simple example. Let's say we have two wires, L1 and L2, and they're oriented in the Z direction, and they're a distance S apart. The first wire is carrying a current I1, and the second current carrying a current I2. What is the force per meter between those wires? So what we'll do is we'll calculate the magnetic field induced by the second wire and figure out what force that puts on the first wire. So rather than take a rigorous approach, let's use the expression for the magnetic field around an infinite wire, because this will make the problem much, much easier. So we will assume that this is the magnetic field around all of the parts of this wire up to the ends, and then the magnetic field outside is just 0. Now we know the magnetic field fringes a little bit at the ends, and we're going to ignore that. So we have the magnetic field intensity H around the second wire, but we need the magnetic flux density in order to figure out the force that it puts on the first wire. So here we have H2, that's the magnetic field intensity put out by wire 2. We use the constitutive relation to put that equation in terms of B2. So it's the same equation, but now there's just this permeability term sitting there. Now that we know B2, the magnetic field put out by L2, now we can figure out the force that that puts on the first wire. So we don't have differential current elements here. These are full long wires, and so the magnetic field is known. We only have one integration to do, so we don't have another differential B field here. So we integrate this just over L1 to get the force that that puts on the first wire. So we plug in our expression for I1 D1. I1 is still just I1, but DL1 is in the Z direction, and of course has a length of DZ. Our B2 field, we derived an expression up here for that. That's the field put off by the second wire. Notice we have some coordinates mixed up here. So what we can do is we can look at the first wire, and if we were in cylindrical coordinates, we know that the magnetic field is in the phi direction. So that we have the phi direction. However, immediately at this second wire, that phi direction is actually in the negative y direction. So as long as we're integrating only along this wire, we can replace a phi with negative ay. And our distance of observation, we are a distance s away from L2, so we can replace rho with s. So we can do all that to this equation, and we end up here. And now this is a cross product that we can do easier, AZ cross an AY. Before I do that, I like to pull out all of the constants so it doesn't confuse the cross product. And so the permeability, the currents, and S, and of course 2 pi, those are not functions of Z. We can bring those to the outside. And now we see we just have a cross product of our 2 unit vectors. So AZ cross negative AY, if we use the right-hand rule, we can figure out that that's actually a unit vector in the X direction, which is also a constant. That can come to the outside of the integral. Now we just have an integral from 0 to L of dz. This entire integral is then just L. So that's our answer for the force. So force per unit length, we had this length L, we'll bring the L over to the other side. And of course it's the F over L, that is the force per unit length. Now on the right, we're visualizing that force. And it turns out the force is actually pushing or pinching those wires together. And this is actually called the pinch effect. And as long as they're carrying currents in the same direction, they will pinch. And you can imagine if they were carrying currents in the opposite direction, they would actually push away from each other. Let's do an example to get a feel for the numbers. Let's say we have 2 wires, they're both carrying 1 amp, they're placed 1 meter apart, and they're 1 meter long. What is the force between them? We actually have 2 ways to do this. We have that equation we just derived, but we made an approximation where there's no magnetic field after the ends of the wire, and on the wire they all follow that same magnetic field for the infinite wire case. So we made an approximation. We can also do it exactly. Let's first do the approximate approach. So this is the equation we just derived, although we moved L back over to the right-hand side since we know length. We can plug in our numbers, and we get 200 nanonewtons for the force between them. That's our approximate solution. We can also do an exact solution and compare the two. Let's see how close they are. So the exact solution, we actually perform the integration. And so I'm converting this unit vector over r squared to the vector r over the magnitude r cubed. That's something that we did a lot in electrostatics. It's a way that I like to do this. So here's our equation, and we can go term by term. If this is an air, then our permeability is just the free space permeability. Our two currents are 1 amps. Both of our differential lengths are dz in the z direction. And we have an expression for R21. In the x direction, they're s apart. And then in the z direction, it's z1 minus z2, just depending where we are in our integral. And then this ratio of R21 over the magnitude R21 squared is this. So here's our equation. We're now going to plug in everything that we know. The constants on the outside stay the same. Our limits of integration will be from 0 to L, and it'll be the same for both wires because they're both oriented from 0 to L. Our DL1 is simply dz1az. Our DL2 is dz2az, and we have that big ugly expression for the ratio of our vectors. The next thing we can do is calculate the cross product inside the parentheses, and we end up here. Then we can calculate that cross product, and we end up here. So if we use the magnetic field that we would have gotten letting the length go to infinity, we got our 200 nanonewtons. That was our first answer. Now performing this integration, we get 82 nanonewtons. So using the approximate approach, we got 200 nanonewtons. Using an exact approach, we got 83 nanonewtons. That is a pretty big difference, but those two numbers are still about the same order of magnitude. So using approximations here, at best we're getting order of magnitude type numbers. Now, just for interest, if the first wire was 1 meter long and the second was 10 meters long, so it's a little bit asymmetric, and we can't use that approximate approach, we have to use the integral, we still get 196 nanonewtons. On to the next subject, force between two current loops. There is really very little difference between handling loops and handling wires like we did before. In fact, the equation for calculating the force on current element 1 due to current element 2 is exactly the same. The only difference is that these integrals are closed contour line integrals, and that's because we have loops. The start of our integration is the same position as the end of our integration. So we have almost the same equation for that force that loop 2 puts on loop 1. We can write the same equation, but for the force that loop 1 puts on loop 2. And this really is the same equation we had before. We just swapped 1's for 2's in the equation. And if we look at this long enough, we can actually see that F2 will be negative F1. That means that the force that one loop puts on the other, regardless of the shapes of the loops, they can be different shapes, but the force that one puts on the other is exactly the same, just in opposite directions. So they'll either completely repel from each other or completely attract to each other. On to our next topic, magnetic torque and moment. I think you'll find this very interesting. So we start with a loop, And it doesn't really matter the shape of the loop. All loops will behave the same, and we'll generalize it later. So we're just letting this be a square loop, and it's carrying current I. Now we apply a magnetic field. And we're talking about a B field here because the magnetic flux density is what is most closely associated with force. And we apply this magnetic field in the same plane as the loop. So at this point, we can now walk around the loop and think about what the force will be. Along this edge, the current is in the same direction as the B field. And remember what happens with force. Force is the cross product of the current and the B field. So if the two vectors are in the same direction, we will get zero. So in fact, there is no force on this part of the loop and this part of the loop. Now when we move to this face, now current and B are completely perpendicular, and we will get a force. And in fact, in this part, the force will be up. On the other part of the loop, because the current is now traveling in the other direction, the force will be down. So if we integrate the total force around this loop, we have just as many forces pushing up as down, and the overall force will be zero. That means if we have a loop in the presence of a magnetic field, there will be no net total force on that. The loop will not move anywhere, so it will not translate its position. However, the forces were different on different parts of the loop. That means the loop will rotate. So it's not translating its position. The center of that loop, if you will, is staying the same, but it rotates. And it will rotate to try to get itself perpendicular to the B field. So we have to have a quick discussion about torque because we have rotating loops. And this comes from mechanics. So sometimes called mechanical moment of force. So imagine we have a rod and we have some kind of cylinder here. And we're putting a force at some distance rho away from the center of this cylinder. So we're applying a force way out here. Well, we describe this as torque. And we will define torque as a vector that'll have its direction down the axis of that rotation, and is defined as R cross F. F being the force that we're applying out here at a distance rho from the center, and R is the vector moment arm. It's really characterizing how far out we are, and it's defined as 2 rho AN, where this is a unit vector pointing in this direction. And it follows a right-hand rule. So if our fingers are turning in the direction that the rotation would happen, our thumb points in the direction of torque. So the vector moment arm has units of meters. Our force is, of course, newtons. That means our torque has units of Newton meters. When we're talking about a current loop, we have to think about what this vector moment arm is. So we have the plane of the loop, and we can define a unit vector that is perpendicular to the plane of the loop. Now this angle is not the angle with respect to the plane, it's the angle with respect to the magnetic field. So AN is always perpendicular to the loop, and if this is the center of the loop, we're at a distance W over 2 actually from the center out to where these forces are applied. So the moment arm is W times AN. And so this R, this vector moment arm, is really conveying how easily that loop can be rotated. If there's a long distance here between the center and those forces can much more easily rotate that loop. Let's go ahead and integrate to calculate the total force across this loop, or applied to this loop. So we'll integrate from 1 to 2 to 3 to 4 and back to 1 again. So we're going to do this closed contour line integral as 4 separate straight line integrals. Let's go ahead and look at these one at a time. So first we're integrating from 1 to 2. That is in the negative x direction. So we have a negative, and it's in the x direction, so our IDL becomes IDX AX. And then the B field is always in the positive x direction. So every mention of the B field is BAX, 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 BAX. Okay, now we're integrating from 2 to 3. That is in the positive y direction. So positive, and then a dy and ay because we're integrating in the y direction. Then from 3 to 4, that is in the positive x direction. So positive, and then a dx/ax. And then last, from 4 to 1, that's the negative y direction. So negative, and then our y direction. At this point, we can look at this and see that we have an ax cross an ax in this integral, and an ax cross an ax in this integral. Well, the cross product of a vector with itself is 0. So in fact, those two line integrals drop, and we're just left with the line integrals in the y direction. So we can bring the b to the outside of the cross product, and now we just have an I dyb with an ay cross ax, and then another ay cross ax here. So if we stare at the picture to the right, we look at our right-hand rule for cross products, y cross x will be a negative az. So when we do that, the negative sign with this az canceled with this negative sign, we end up with a positive. Likewise, the negative associated with the az came out, and we have a negative. And we can bring the az unit vector to the outside of the integral, so we're just left with ibaz times one integral with an ibaz times the other integral. And that's easy to evaluate. These are both length L. So same term being subtracted, we get 0. So this is really telling us a bit more rigorously that there is 0 net force on this loop. However, different parts of the loop have different forces, so it does put a torque on the loop. One thing we can come away with is that these calculations are a bit complicated, and we would like a way to simplify them. Well, one way to simplify them is to come up with something called the magnetic dipole moment. And this lumps everything there is about that loop into a single vector. And it lumps together everything about that loop that would affect how it rotates in the presence of a magnetic field. Well, what are the things we need to consider about that? Well, how much current the loop is carrying, the cross-sectional area, and the orientation of that loop. This AN is a unit vector perpendicular to the area defined by that loop. So for a planar loop, and by the way, it's possible to have a loop that kind of meanders like a roller coaster, but that's a more complicated analysis. So for any planar loop, this magnetic dipole moment turns out is independent of the shape of that loop. It's just the current times the cross-sectional area in the direction perpendicular to the area defined by that loop. And it has units of amp meters squared. And so everything about that loop is lumped into M, so it's just a quick, simple calculation, a cross product with the applied magnetic field to calculate the torque that would be rotating that loop. So it's a very convenient way to simplify our math. And just one other thing, let's look at the magnitude of that torque when we think of this angle alpha, because the B field really could be at any angle relative to that loop. And we see that there's a sine alpha there. Well, this sine is maximized when alpha is 90 degrees. So when the B field is in the plane of the loop, that's when we get the maximum torque. When this is 0 degrees, in other words, the B field is punching straight through that loop, that's when we get 0 torque. So this equation is really nice to just sort of help us visualize how the torque depends on the orientation of the field, the current, the cross-sectional area, and the B field. Let's do an example to calculate the magnetic moment. So here we have a triangular loop carrying a current I, and in this case it's 4 amps, and we know the positions of the different vertices. What is that magnetic moment? Well, our equation is ISAN for a planar loop. And in this case, it's a triangle, so it has to be in a plane. Well, we're given that the current is 4 amps, so that's an easy one. What is the area of that triangle? Well, remember back when we talked about vector calculus, the definition of a cross product is that it's the area of the parallelogram defined by A and B. So if we want the area of the triangle, that's half of the parallelogram. So the area is just 1/2 A cross B. And we can calculate A and B by knowing the positions of the vertices in the triangle. So we can calculate A and B. I picked this point along the x-axis to sort of be the common point. So vector A is this vertex minus this vertex. Vector B is this vertex minus this vertex. And so now we have A and B. So now it's real easy. We just calculate the cross product, and 1/2 the magnitude of that cross product gives us the area. The area of that loop is 3.5. And if we were doing units of meters, that would be 3.5 meters squared. The surface normal, how do we get that? Well, we have these vectors A and B, and so the vector perpendicular to that triangle is in the same direction as the cross product of A and B, because A and B lie in the plane of that triangle. So the cross product is in the direction perpendicular to the loop, but we need a unit vector, so we have to divide by the magnitude of that cross product. So we can go ahead and throw in our numbers, and we have an answer for that normal vector. So altogether, that magnetic moment is I times S times a unit vector perpendicular to the loop. We plug in everything that we have, and we get our final answer for the magnetic moment. And again, units, amp meters squared. And I'm kind of lazy here and dropping the units, and that because I do that because it tends to crowd the slides, but that's bad practice. This is an example of do as I say, not as I do. Carry the units throughout here, and then you'll get less lost. Very last topic, a quick topic that I'm not going to go into a whole lot of detail, but it's talked about a lot, so I would like you to see it. It's called the magnetic dipole. There is no such thing as a magnetic monopole, so we talk about magnetic dipoles all the time. And a little tiny loop actually gives us a magnetic dipole. It gives us a little tiny magnetic field through the center of that loop. So if we have a very, very small loop with radius A, we can go back to our equation for the magnetic moment and calculate what that is for a very small loop. Pi a squared, that's the area, so this really is just our S in our previous equation. And we have the magnetic moment of a small loop. Given that, we can calculate the B field around that. And here's the equation in spherical coordinates to calculate the B field at any point due to that small magnetic dipole.